Hi everyone, this is Miss Moriarty and I'm here to discuss with us topic 3.3 all the way to topic 3.5 in our unit 3 of our notes. So make sure as you watch the video, make sure that you are jotting down notes. Okay, here we go. So topic 3.3 is all about survivorship curves. And this is actually what we were trying to demonstrate in our survivorship bubble lab that we've been doing the past 2 days. So, what is a survivorship curve? It is a line that's going to show the survival rate of a specific cohort, which typically means a group of the same aged individuals in a population from their birth to their death. We can see that the faster we see a drop in the line, typically the quicker the die off of individuals in that population, versus a slower drop in the line, we oftentimes see a longer average lifespan from their birth to their death. So you can kind of see in type 1 here, they tend to have very long lifespans, high survivorship at early stages of their life because they tend to provide parental care, versus type 3, which is just the opposite. They don't really provide any parental care. We tend to see very high mortality, very low survivorship at very early stages of life. And type 2 here, we can kind of see that they have a linear survivorship throughout their lifetime. So, going into a little bit more depth with each type. So, a species that practices type 1 survivorship usually is K selected. They have high survivorship early on in life due to the parental care. That high survivorship in midlife continues due to their large size and defensive behavior, but we see a rapid decrease in their survivorship later on in life as old age begins to set in. And it's most mammals that tend to show this type of survivorship. Type 2, this can actually be an R or a K species. We can kind of see a steady decrease in their survivorship throughout their life due to many different types of factors. While type 3, which is mostly R selected species, they tend to have very high mortality, so low survivorship early in life because they don't provide any parental care. Few tend to make it to that midlife, and we kind of see a slow and steady decline throughout their survivorship in midlife, and even fewer can make it to adulthood. So we see a then slow decline in survivorship in their old age. Some examples of species that show this type of survivorship is things like insects, fish, and plants. Now, remember the three topics we've now discussed, right? A specialist versus a generalist, an R versus a K, and survivorship curves. These are all, remember, reproductive strategies or characteristics about species that are going to, over time, influence how they're going to grow and how that population is going to respond to certain changes. So moving then on to 3.5. 3.4. This is carrying capacity. This is probably a word that you've heard before in other biology classes. But carrying capacity means the maximum number of organisms that can be supported in a given area due to any type of limitation of that resource or even competition. Some examples of things that might be limiting resources could be the food, water, habitat, even maybe mates. And when a population ends up exceeding its carrying capacity, an overshoot is going to occur. You can also see on this graph to the right, we've talked a little bit about this before, but don't forget, typically at the beginning of a population's growth, they tend to show that exponential growth, which we know can also be called a J curve. When that population tends to hit the carrying capacity, it displays an S curve, which is now known as logistic growth. And so here we tend to see logistic growth in K-selected species, and when they hit their carrying capacity, it's going to fluctuate. So what is actually happening in a population when it goes beyond its carrying capacity? Well, we see overshoot occur. So this is when a population is going to briefly exceed its carrying capacity, and what you're going to see then happen is the population is going to crash. Some examples of that might be deer tend to breed in the fall. They give birth all at once. Then in the spring, we tend to see a sudden spike in their population. They overshoot above their carrying capacity. And as a consequence, we see resource depletion. Now we see overgrazing of deer. There's not enough food available. So their population numbers decrease, and we see what's called die off. So that's going to be a sharp decrease in its population size when that resource depletion is going to occur. And as a result, we see many deer may or may not starve with too many new fawns feeding in the spring. And so their population will fall then below the carrying capacity. And when it does that, now resources can become plentiful once again, then the population will continue showing that type of pattern. Now in topic 3.5, this is once again analyzing more population growth, how populations group one another, and how resource availability may affect that. So some other key pieces we need to know when studying populations is the size, right? The total number of individuals in a given area at a given time. The larger the population usually is safer from population decline. The density number is usually the number of individuals over a given area. High density typically means high competition, more likely for disease outbreak, and maybe even possibility of food depletion. Now, these can be influenced how the population distributes itself in that then area. And there's three types of distribution here. One is random distribution, which is often shown with vegetation and plant species due to seed dispersal. They can randomly fall in different areas, versus a uniform distribution. Species tend to show this type of distribution because of competition and territory, while a clumped distribution is a result of predatory behavior. So oftentimes this is where we see animals end up in groups or herds to either hunt or maybe keep themselves safe from other predators. And so how they distribute themselves can certainly affect the density and can also affect then overall the growth. Some other factors we need to take into account is the sex ratio amongst the organisms in that population. And this means the ratio of males to females. And the closer to that 50-50 ratio, the more ideal breeding will be. When that ratio is off, as a result of die-off or maybe even a bottleneck effect, this can lead to a skewed sex ratio. Maybe there's not enough females to mate with the number of males, and this is going to limit the population growth. And this is where we get into factors that can influence that population's growth. One is density dependent factors, while the other is density independent. We did kind of touch upon these when we talked about R versus K, but going a little bit more into what they mean, a density dependent factor is something that influences the population growth based on its actual size. So this would be the food available, the competition for the habitat, the water, light available, maybe even disease. Because remember, the more people there are in a given area, the more likely that disease is to then spread. So all of these things will limit its population growth based on its size. So small populations don't really experience these as often as maybe a large one would. While a density independent factor are factors that are influenced independent of the population's size. So this would be a natural disaster like a flood, hurricane, tornado, earthquake, fire. Doesn't matter how big or small the population will be, the natural disaster will limit them in any way possible. So just further going into examples of density dependent factors, we can see in the graphs here, we had two different types of organisms placed in the same environment here. So under low food conditions, we can see that the populations of species tend to grow rapidly at first and reached a kind of plateau. That must have been their carrying capacity. But with twice as much food available, we saw that the populations actually then grew twice as large, but then still reached that plateau. So it's important to note that when we talk about food as a density dependent factor, when food availability becomes even more plentiful, that population has the ability to increase its carrying capacity. The last slide of our notes video today, and this is about calculating population change. So here we want to actually see, well, how much did the population change as a result of the factor that we were analyzing? So you want to use the formula written here, population size equals the immigration plus birth. So this is the number of individuals adding to the population, minus your emigrations and death. So this is the number of individuals subtracting from the population. So an example here would be an elk population of about 52 elk, have 19 births and 6 deaths in a season, while 5 new elk immigrate to the herd and 0 elk emigrate from the herd. So here, if we place those numbers into that same formula there, we can see that there was an addition. We can see now our population size is up to 70 elk because now at least 18 elk were added to the original. All right, everybody, that's it for this video. Remember, you have till Friday morning to watch, take notes, and please mark it as done when complete.